And I'm going to share my screen. So good afternoon, everyone. And today's topic is about linear mixed effects model. Well, previously in August, we touched on how to do exploratory data analysis, and today how we do model fitting and checking, although almost all of you have done already. And before we go on, there is some administrative information. So this session we had on Thursday at this time, but from October, we are going to shift. Well, we are going to change the time and date. It's going to be second Friday between 12:30 to 1:30 in Philadelphia time. And this information can be seen in team calendar, well, and in the next slide, and also Google Drive of this session for these sessions. And Zoom link also will change. So the Zoom link you have to participate in today won't work anymore for the next time. So be careful. And well, this information, Zoom link is also seen in Salvar calendar, also in the next slide. And all presentation slide recording. And also I didn't mention the codes used in producing graphs and tables and analysis. They are also in the folder. So please utilize if you are not aware of it. And also if you, well, previously I didn't do this, but I saw that this is more convenient. And if you want to receive email about the sessions, like a reminder or next topic, etc., please email me so that I can send you reminder answer to you. And if you have any question, let me know. And this is a schedule, and we are in number 3. And next time we are going to work on, well, still linear mixed effects model, but with random slope. And afterward, I'm going to touch on logistic mixed effects model. And afterwards, I haven't decided what's going to be touched. But these are the list which I may touch. But if you have any suggestion about the topic we should touch, please let me know. Do you have any question up to now? Okay, I hear silence. Please, if you have anything, please let me know. Also, when I'm doing this presentation, if you have a question, just interrupt me and you don't have to wait up to the end. And also, sometimes I miss chat, so please speak up. Or somebody tell me that there is something in the chat. Okay. And today's topic is this one. It's about model fitting and checking. And today also, we are going to use example data. Again, it's from Mexican National Health and Nutritional Survey, which is ENSANUT 2016 for adult population. But this is not a real data set, as I mentioned previously. I changed city ID and also I changed values. So don't use this data set, which you can find in the folder I mentioned previously, because they're not real. And this is just prepared for this purpose. And the sample size with the data set contain about 4,000 individual records. And these are variables we can find or we are going to use in the following presentation: city ID, sex, age category in 10 years, SBP for systolic blood pressure, BMI, and population, well, city population in 10,000. And for study aims, we try to answer these 2 study aims in the following. One, we want to assess sex and age difference in blood pressure, which is measured by systolic blood pressure, accounting for for BMI, which is given by this equation. And we are interested in how the coefficient for sex, age, and their interactions after adjusting for BMI in this equation. And the second one, if the sample size, city size has association with blood pressure. So I just added city level population size here, and we are interested in this coefficient beta 5. And just a notation, IJ, SBP IJ represent systolic blood pressure of CDI of person J. So far, so good?
Yeah, so this is at the individual level, Goro?
Yep, it's individual.
Thanks.
And previously we did this EDA, and we did how we do this EDA to assess the following three things about clustering, nesting structure, mean components, variance component. But this part I'm going to skip. So if you're interested in, please just go through the slide, and which should be very self-explanatory, I think. Also, I may explain a little bit some of them, since it will be important when we start modeling. First of all, we have about 4,000 individual records, which come from 59 cities. And the smallest city, smallest or largest in terms of number of observation we have. The smallest city has 7 individual records. It's quite small. And second smallest, 10 individual within a city, and so on. And the median size is 39 individual records per city. And the biggest one is about 950. And this is a histogram that shows the number of observations per city. As we saw in the table before, there is one city with large sample size, 950 per city, but majority have sample size less than 100, and many of them 50 or lower. And then afterwards, I checked linearity of these variables. Well, but this part I'm going to skip, since we covered this topic last time. So we go to this model fitting part. We are going to consider these 4 models in the process. So first model is going to be, well, intercept only model, which includes only city level intercept plus residual. And then in model 2, we add, well, demographical characteristics, which are sex and age and their interaction term. Well, there may be difference, I should say, there might be interaction between sex and age. We do not know, but we want to know what are the differences, or if there are no difference. Well, we want to know anyway the differences. So yes or yes, we are going to include their interaction term, regardless of their significance. And then we want to know the sex and age specific association with systolic blood pressure after we adjusted for BMI. So we include BMI in model 3, and model 4, we want to also know if population size, city population size also have influence on individual systolic blood pressure. And variable management selection, age will be included as a categorical variable. When I did assessment, well, age is roughly linearly associated with systolic blood pressure. So we can include as continuous variable, but in this example, I just decided to include age as categorical variable. And BMI as a continuous variable after I assess linear association between SBP and BMI. And interaction between sex and age will be included independent from its significance, as I mentioned. And the interaction between sex and BMI will be assessed and then included if it's significant. And in this process, we don't do any variable selections, and these variables are selected a priori. And sometimes we do model fitting, say when we have a lot of factors which we think they are associated with blood pressure, but we don't know. And our study aim is to identify factors that are mostly affected with blood pressure. In this case, we may have to do variable selection, but this time we don't do that. And do you have any question about now analysis plan? Okay. And then this is model 1, which is no model. This is output from both package from Stata. First of all, the number of observation, it's 4,059. We make sure that observation is as expected, and which are coming from 59 groups, meaning 59 cities. And as we saw previously, observation per group, observation per city, the minimum is 7 observations per city, and the maximum is 953 observations per city. And this one, I think I'm going to use a pointer. So this is a model equation which I presented previously. So systolic blood pressure is given by city-specific intercept plus residual. Residual is the difference between city-specific mean and individual blood pressure. And city-specific intercept can be divided into 2, beta naught, which is a global meaning as a whole in this country, in Mexico, what is the mean blood pressure, plus random intercept, BI, which is the difference between global mean or national mean and city mean. Well, I said national mean, but national limited to Salzburg cities, plus residual. And this is the output, and this estimate for beta naught global mean. You see some this triangle on top of beta, which means, which I had, and which mean estimated value, not a real value, which is 120. So the global mean is systolic blood pressure of 120 millimeter of mercury globally in Mexico. And there are two more outputs here. The first one shows estimated standard deviation for random intercept and the estimated standard deviation for residual. And what do they mean? I'm going to switch my stuff. Well, I need this information as well. Okay. First of all, let's talk about, so it's small. So we talk about this one. What do they mean? So we take, systolic blood pressure on the horizontal axis, maybe systolic blood pressure bar, meaning distribution of city mean. And we assume that systolic blood pressure is normally distributed, and estimation of its standard error is or was this one, 3.499. So it's roughly 3.5. Standard deviation, estimated standard deviation is 3.5. So it means that 2 standard deviation is roughly 7. And in this graph, well, here the peak is going to be global mean, which was 120. Okay. And then distribution with 2 standard error of 7. So it means that 95% of the city, the mean of among 95% of the city, its mean systolic pressure will be within plus or minus 2 standard deviation, which is 7 from here and 7 from here. So, and the global mean is 120. So it's 95% of time we expect city mean between 113, which is given by 120 minus 7, and up to 127. Well, I should write a bit better, but anyhow. So this is what we get from here, from this estimate. And how about residual, which says 21? So again, we take systolic blood pressure on the horizontal axis, and here is a city mean. And according to the estimations, estimated standard deviation for residual was roughly how much was it? Was it 20? So it was 21, okay. 21. So 2 standard deviation is going to be about 42. So it means that, first of all, this residual, we assume that it's normally distributed. The peak is somehow, the peak should be around the city mean. And then 95% of the time, the residual, which is a difference between individual blood pressure and city mean, is distributed in this way. So 95% of time we can find within plus or minus 42 from the city mean. So as we can see from, well, by comparing these 2 things, we should expect more variability in blood pressure within city as compared to between city. Do you have any question here? Okay, so I go on to the next slide. So this is from new model, and then now we add sex, age, and their interaction term, and we confirm that sample size is the same as previously, always we have to make sure that we have the same observation. Otherwise, we cannot compare models. And well, the model equation is given here in red. And well, okay, these are coefficients for age category, for sex and interaction term, And then we look at this one. This is a global test for interaction between age and sex. Because we have 5 age categories, we included 4 age category dummy variable. So this is the reason why we have 4 components here. And the p-value was less than 0.001. So which means that the association between age and blood pressure differs by sex, or vice versa. The association between sex and blood pressure differs by age. Okay, then let's include BMI now. So I included BMI as well as the interaction terms. So this model equation presented here is wrong because I need to include interaction term between BMI and sex here. So I run the model, and then coefficient for sex, age, BMI, interaction time between age and sex, and interaction time between sex and BMI here. And then this is a result of test if there is interaction between BMI and sex. Well, this result is identical to this p-value because there is only one term included. So in short, the association between BMI and systolic blood pressure is different between male and female, between men and women. And what to do next? Well, here we have an option to fit separate model, one for men and the other for women. Or we can do in this way. And well, there are pros and cons. But for this example, we assume that we decided to use only one model, which includes interaction between age and sex and BMI and sex. Then finally, to answer the study aim 2, we included population size, and this is a coefficient. Well, since the population was skewed and it was log transformed, and its p-value was 0.5, so it was not significant. So population size didn't affect individual level systolic blood pressure. And model presentation, this is one way to present. There are several ways, and this is how I may present if I need to use table. And well, when we have interaction terms in the model, it's usually better to present coefficient in a stratified manner. So here you can see what is the effect of age for men and what is the effect of age among women. Instead of showing estimated coefficient for men and interaction term between age and sex. And the same thing, well, here I present BMI for men and women. And we can also utilize graph to present the same data. Oh, and then, well, this coefficient for women, well, men was reference group for sex. And these values for women, these were given by, well, value, I'm meaning these values and these value for sex. So these coefficients were obtained by linear combination of estimated coefficient. And one more thing about the interpretation. Well, let's look at the example of this part, this 18 from model 3. It's going to be a bit wordy. But so for this list, I wrote, for a given city, among the male population of 6 years or above, systolic blood pressure was 18 millimeter of mercury, higher than male population of 20 to 25 years on average after adjusting for BMI and city population size. Well, long one, but what is the difference between in interpretation between usual linear regression model and this mixed effect model, which is this one, this underlying part for a given city? This is a difference. Why we have to say for a given city? It's because of this equation. This equation includes this city-specific intercept. So what does it mean? Blood pressure will change depending on which city you live in. So if we do not fix a city, and when we observe difference in blood pressure, we do not know if it is because I live in different city or because of my age and so on. So when we say so, when we want to interpret coefficient of beta 1 up to beta 4, we have to say that we fix beta not I, which can be said by this term, this expression for a given city. And in case of linear regression, actually, if we do the same modeling using GEE, we are going to get the same or very, very, very similar estimation. So actually, it doesn't matter to say for a given city or not, but we are using mixed effects model. It's better to say so. And although we are going to talk this one more in detail when we cover logistic regression, this value, the coefficient or odds ratio are going to be different when we use mixed effect model and GE model. And it's quite important to say for a given city. Do you have any question up to now? Okay, silence.
Goro,
Aha.
sorry. This is Firmino.
Firmino.
Goro, I have a question regarding the population, comparing population of 20 to 29 years. Where in the model you put that this is a reference term?
So age consists of 5 categories, right?
Yes.
And when you see the output, well, I went to model 2, but it doesn't matter. So you see only four categories here. Right?
Yes.
In the output. So it means that 22, 29 is a reference category. So this coefficient means, for example, this one 4.26 is a difference between 30 to 39 as compared to 22, 29 for male population. I added male population because we have interaction time.
Yes, and about the interactions, it is important to make the interactions only in a categorical variable. We need to okay, categorize.
Good questions. And it's also depending on if you want to interpret or not the coefficient. If it is just for adjustment purpose, it doesn't matter. But usually we include interaction term because we are interested in the interaction of specific variables. And in this case, it's usually better to have interaction term between two categorical variables or one categorical and the other continuous. So actually for this reason, I included age as categorical and BMI as numerical for the presentation purpose. So for here, for BMI, sex is categorical and BMI is continuous. And for age and sex, they are both of them categorical. But continuous times continuous, it's somehow very difficult to interpret or present. At the same time, continuous times continuous interactions, we don't see much in real life. Did I answer to your question?
Yes, thank you, Goro.
You're welcome. Thank you for your question. Any more questions?
Yes.
Hi, Jenny.
Hi, Goro. Yes, I wonder if how do you estimate those coefficients of that table? I think that did you use the Lincoln command or
Yes. Yes, they are given by linear combination. For example, let's go back to the previous. So this is a full model. So for BMI, for male, this is a 6.7. This is for male. And for women, I added 6.7, and its interaction time is negative 3.2. And by adding these two, we get estimate for women. And similarly for age, for 30 to 39 age category, this 2.95, this is an estimation for male population, and female population, I added 2.95 and 2.66 for women's population.
Thank you.
You're welcome. And also, as I mentioned, well, the codes are available in the data. I included the codes in the session website. So please go ahead and then look at it, and you can see exactly what I did. Just in case, this is
Okay. Thanks.
This is the course website. Well, it's syncing. Course website, and for example, this is the sessions folder. For unknown reason, it's not responding. Okay, it's responding. And then you see data set as well as script or do file or program, so you can look at it how I calculate this value. Okay. Any more questions? Okay, let's go. And model checking, which sometimes we don't do, and we forgot to do, but it's always we have to do model checking because we do modeling assuming some assumptions. So first of all, we check about fixed components and then random components. So residual versus fitted plot, and this is almost the same as what we do for usual linear regression model. And this one, what are the checkpoints? So this one, vertical axis, which shows a residual, and horizontal axis shows a fitted value. And what do we see? First of all, we look at the overall fit or linearity in all covariates. And if this assumption holds, we expect that the mean of residual are always constantly around 0, as you can see here. But by the way, this red line is the lowest curve, which represents a mean of residual at each fitted value. So here it's almost linear, so it means that this assumption was okay, hold. And normality of residual, so around 0, are they scattered normally? Well, somehow difficult to say if it is normal or not, but we see that more clouds here and then less clouds outside. Although we see some, per se, more residual at higher end as compared to lower end. And equal variance of residual by checking if the scatteredness or if the residual are scattered around similarly across fitted value. I think it's okay. And sometimes we may see funnel type, like at lower fitted value, we see small variability, and then at higher level of fitted value, we may see higher variability. And in this case, we may have to do something else, but something. But in this case, we can assume that, well, they are distributed evenly across all fitted values. Then residual versus predictor plot. In this case, I plotted sex. What? Hold on. Residual. Okay. Residual versus predictor. Well, it's not well. It's not really residual. Well, I explain what I did. So first of all, I fitted the lowest curve on systolic blood. Well, I calculated the mean systolic blood pressure at each age categories, and they were just connected using line. And blue line, I calculated fitted value, and I fitted lowest curve on fitted values. And as you can see, so the red line is based on observed value, and the blue line based on fitted values. And then we expect that they overlap well if the model fits well to our data. And as we can see, we see red and blue line together. So linearity assumption for this categorical predictor, which is age category, is okay. Do you have any question about it? I think I will rewrite this slide and update the revised one so that the title is not confusing. And this one, the same thing for BMI, and the blue line was lowest curve on observed value. And observed association was expressed using blue line. Blue line. And I also fit the lowest curve on fitted value of systolic blood pressure. And this blue line also go along very well with lowest curve on observed line for male and female. And we see some departure here for male and female, but we can ignore this because this lowest curve on observed is very influenced by these small outliers. And this is for population size, and this is the same as previous thing, which is for BMI. So I skip it, and we can see that blue line and red line, they are almost identical. So we can be sure that our linearity assumptions are all holds. Do you have any question up to now? Okay, now this is somehow specific to mixed effect model. So we can estimate city specific intercept or random intercepts. And well, this is a histogram of 59 random intercept. Well, because in our model, we assume the random intercept distribute normally, and we should see normal distribution of random intercept. And then I also added 2 vertical line, which represent minus standard deviation, and 2 standard deviation, which I was explaining using hand-written graphs. The next one, about the shrinkage we talked about previously. Ideally, we are supposed to use we are supposed to do this using full model, but if you remember, per city, some cities or many cities have very small number of individuals. For this reason, we cannot fit the full model for each city. For this reason, we cannot do this assessment. So this is a checking of shrinkage using null model as proxy. Well, this is the reason why I said that this is to have rough idea. And this blue dot, which show, by the way, this vertical axis show city average systolic blood pressure. And from 1 to 59, these are city IDs starting from 1 to 59. And the blue dot shows observed average. Well, it says maximal likelihood estimate, which is equal to just a mean using the observation in the city. So if there are 10 observations within the city, this blue dot is given by averaging these 10 systolic blood pressure values. And the red one, these are city-specific mean estimate from mixed effect model. As you can see, always these are, by the way, these are black solid line shows overall mean, global mean, or national mean among several cities. And always this red dot, well, city means estimated by mixed effect model is always, let's say, between observed city mean and global mean. And the level of, how they were shrunk towards a global mean differs. Sometimes it's big, sometimes not big, mainly because of sample size. And we use the same data set, but plotted different way. So here the vertical axis shows observed systolic blood pressure mean of systolic blood pressure. And vertical axis shows, it's vice versa. Horizontal shows observed blood pressure, observed mean of blood pressure, and the vertical axis shows estimated city-specific mean. And if they are identical, we should see the dot on top of this identity line, but which is not. So, for example, this city has very small sample size. By the way, this one circle represents one city, but the magnitude, the size of circle is proportional to population size. So if the circle is small, it means that sample size per city was small. So for this city, the observed mean was 142 or something, but its estimated mean was around 123 or 4. And similarly, for this city, the observed mean was 134, 135, but estimated mean is about 125. And for lower end, for this city, the observed mean was somehow less than 110, but estimated mean is 115. So what does it mean? So by modeling, well, if the city have only 7 people in the city, well, the question is, can we estimate can these 7 people represent entire population of the city? Maybe not. So what shall we do? Well, let's borrow the information from other cities, and then we re-estimate the more likely city mean of systolic population. This is how it works. And lastly, interclass correlation. This one shows what the black dot shows a residual, which is given by observed value minus fitted value. And red dot, which shows random intercept, which is city average minus overall mean, overall average. And also I superimposed plus or minus 2 standard deviation for random intercept and residual. And as you can see, the variability between city, which is given by variability of random intercept, is much smaller as compared to variability of residual, which shows the variability of within city variability. And when we calculate ICC, it's 0.03 for this example. Do you have any question up to now? Silence. Okay, so this is summaries of today's session. So we reviewed model fitting and checking procedure for linear mixed effects model. So principally, the process is very, very similar to those for usual linear regression model, as you could see. And only the difference is we need to do assessment of random components, which doesn't exist in usual linear regression model. And also, I forgot to put here, and the interpretation coefficient is slightly different from how we interpret when we use usual linear regression model. And this is the end of today's for today's session. And next session is going to be on Friday, October 8th, between 12:30 to 1:30 in Philadelphia time. And the topic we are going to cover is linear effects model, linear mixed effects model with random slope. And then afterwards, we move to different models, which are logistic or Poisson or negative binomial. Okay, thank you very much for your attention. And I wonder if you have any questions for clarification.
Just wanted to congratulate you. This has been very, very helpful, really interesting and clear explanations. As I've said, I'm a real fan of how you're presenting the shrinkage effects and the ICCs, and I think this is really, really clear, very instructive.
Thank you, Uriel. Okay. All right. Thank you very much, everyone. So this is end of today's sessions. And then if you have any questions which you couldn't ask, or if you get questions afterwards, please feel free to email me. And thank you very much. And see you next time.
Bye.